Hello, everybody, and welcome back. In this segment, we're going to start taking a look at something known as interval estimation. Basically, what interval estimation is a technique that allows us to place some range of error around a particular estimate, given that we are aware acutely now that as we look at different samples from the population, each sample is a little bit different because we're trying to randomly sample. And that would lead to a little bit of sampling noise when we're trying to do something like estimate the sample mean of our population. So let's not forget about the estimation process itself. This is a process where we're taking a population, some group of interest. We are looking at a subset of that population, a smaller subset, because looking at the entire population may not be feasible or may be very costly. And what we're going to do today is we're going to think about making a statement similar to what this gentleman is saying here. He's saying, I'm 95% confident that the true population mean mu is between 40 and 60. So it looks like he estimated that the average was 50, X bar was 50, and he's given himself a margin of error of about plus or minus 10 around that estimate. So plus 10 brings him up to 60, minus 10 down to 40. And this is really what we want to be able to do. We want to explain where the 60 and the 40 came from in this situation. Where did he get the upper and lower bounds? So it's important at this point to define the difference between a point estimate and the interval itself. And a sample statistic is used to estimate a population parameter. So again, in terms of our measures of central tendency and our measures of dispersion, the population parameter we were using to describe the center was the mean mu of the population. The variance was sigma squared. And then we had utilized some sample statistics in a way where we were kind of thinking about X bar as our best guess as what mu would be. And our measure S squared here, the sample variance, was our best guess given the sample data at the actual variance, which is sigma squared. So again, point estimates here, they are providing us with a single value. They are based on one sample in particular. If we had sampled a different set from the population, we would wind up most likely with a different set of sample statistics. And what we want to do is provide a little bit of context to that point estimate by giving ourselves a margin of error around that point estimate. How certain are we, or how uncertain are we? So here's a real quick example. In an effort to improve its drive-through service here, Burger King records the drive-through times of 52 randomly selected vehicles, and it finds that the sample's mean service time is about 181.3 seconds for those 52 vehicles. And again, if they had sampled 52 different vehicles, they would probably get a slightly different sample mean. And the question here is now, how close is that value of X bar relative to the unknown population parameter mu? And this is a strange catch-22. Because we're never really going to know the underlying population mean mu. So we're trying to guess something, right? We're trying to shoot at the middle of a target, and we can't even see the bullseye. So it's a strange place we find ourselves in statistics in general. There's some underlying data generating process or some underlying population that we can't observe. And we're trying to use some remnants of information from the sample of that population in order to make the inference about that population itself, which again, we'll never actually know. So a point estimate, first and foremost, it's only good as the sample it represents. Other random samples from the same population are likely to result in different point estimates because we're sampling randomly. The likelihood I'm going to sample exactly the same observations from the population again is very low. So because there is some slight variability in these sample statistics due to the heterogeneity in which data we're sampling from the population, this is why we want to also include a confidence interval with our point estimates. So not only do we understand where we think the parameter value is, but we have some idea of how much noise there is in that sampling process. So the confidence interval itself is going to provide us with a range of values, which we feel some confidence in which the population mean might be located. It takes into consideration the variability in the point estimates from this sampling noise from sample to sample. So here's a general picture of what we're trying to do. Okay, we have our point estimate right in the middle of this range. Okay, and we're now trying to figure out how can we construct this interval here, okay, by identifying a maximum interval value, sort of an upper bound of that threshold, as well as a lower bound. So that is the goal. You've probably seen confidence intervals in other situations. Here's a slide that shows EPA fuel estimates, right? 15 to 21 miles per gallon. They're telling you the average is 18, but they're giving themselves a margin of 3 miles per gallon up or down here. Highway miles per gallon, again, they're giving us the point estimate is 25, and they're showing us there's an expected range between 21 and 29. So it looks like they're giving themselves about a 4 mile per gallon margin of error. Again, you can see a very similar one here for the SUVs. 21 miles per gallon on average is the center of the distribution of their point estimate. And they give themselves a margin of error of 10, about 10, 10 above, about 10 below here. So all these cases, we can kind of think about a margin of error being associated with our particular confidence interval. So in order to construct a confidence interval, the first thing we need to specify is something known as the confidence level. And this is really somewhat of an ad hoc specification in that there's not a general rule of thumb. Well, there's a general rule of thumb rather, but this is a user specified value rather. This is not going to be determined from the data itself. So if we were interested in a confidence level of 95%, okay, the interpretation here would be that we are 95% confident that the population mean mu is contained within the interval that we're going to construct. Now, this doesn't mean that there's a 95% probability that mu falls within the interval that we construct. This is actually a very classic mistake that folks make when interpreting these intervals. The proper way to think about a 95% confidence interval when we construct it is that if we were to construct 100 of these confidence intervals by sampling 100 different samples from the population, each sample being slightly different, right? Each sample is going to have a slightly different X bar associated with it. Then out of 100 samples, about 95% of those would contain mu, while approximately 5% would not contain mu. Okay, so we're gonna, in the next video series, we're gonna actually go through the process of how to construct this. I'm gonna give you a little peek here in a moment, but here is a sampling distribution. Here we have the expected value of X bar right in the middle of the sampling distribution. And it looks like here we have calculated an upper bound as well as a lower bound. And the sizes of the upper bound and the lower bound are going to be defined by those tail probabilities in yellow there. And we're going to go through the process of actually constructing the interval in the next video segment. But you can imagine, depending on which data we've sampled, right, the means could be a little bit different. So here is a particular sample where the mean is X1 bar. And you'll notice with that sample, we've also included a confidence interval. Okay, and if you imagine this vertical dotted line here as being the true population mean, because we know on average, the sample mean is an unbiased estimator of the population mean, then it looks like even though X1 bar is a little bit far away, not totally far away, but a little bit from where the true mu is, it's not a perfect point estimate. But you'll notice now that we have the confidence interval shown here graphically in the distance of this, this line, okay, we can see that that particular confidence interval does happen to contain the population mean mu. Now, if we had sampled different data from that population, like suppose we take sample 2 and we calculate a mean of X2 bar, and then we calculate a confidence interval for X2 bar, you'll notice X2 bar is a little bit lower than the population mean, as denoted by this vertical dotted line here. Okay. That being said, the confidence interval in this picture looks like it still contains mu. It's captured mu inside. And we could think about repeating this process. Here's another sample, X3, slightly different sample mean again, because there's some sampling noise. And the confidence interval looks like it contains mu. Here is another one. It also contains mu, but you'll notice it's possible, depending on the sample of data that we have, it may not be very representative, that we could construct a confidence interval. And this confidence interval here associated with the sample mean, the point estimate x5, that does not contain the true population mu, which is all the way over here again on this vertical dotted line. So if we were thinking about constructing all these different confidence intervals, okay, suppose we did this, 100 times like we thought of in the last slide, then the way to interpret a confidence interval, okay, it's not that the confidence level, right, that 95% level, that doesn't mean there's a 95% chance that mu falls inside the confidence interval. It means if we repeated this process, x1, x2, x3 bar, 4, 5, 6, if we did that 100 times, we had 100 samples, then on average, 95% of those intervals would contain the true population mu, and 5%, alpha percent rather, would not contain the true population mean mu. So this is a very, very important part of understanding the confidence interval. The confidence level is not actually associated with the probability that mu, the true parameter, falls within our error bounds. So a confidence interval either does or does not contain the true population mean mu. Okay, there is no probability involved in a specific interval in terms of the probability that mu falls inside of it. Okay, it is not certain that the population mean is in the interval. Really, only in one case can we say this, and that's if we had a 100% confidence interval. But as we'll see momentarily, when we think about constructing a 100% confidence interval, that would wind up being infinitely wide. So your bounds would go from negative infinity to positive infinity. In that case, of course, it's going to contain the true population mu. But in that regard, it winds up being meaningless to think of a error range that large. So a higher confidence level, this will lead to a wider confidence interval. And this sounds nice in that you're more likely to think about capturing the true mean in that interval. However, the wider the interval is, the less information more often is provided. So we can see that in this next example here. Okay, so in scenario one, we have an estimate with 99% confidence that an accountant's average starting salary is between $15,000 and $100,000. In scenario two, we would contrast that with a 95% confidence interval, so a little bit less confident. Okay, but now you'll notice that interval estimate is much smaller, right? The starting salary lies between only $42,000 to $45,000. So we only have a confidence interval of length 3,000, meaning we gave ourselves a margin of error of about 1.5 thousand on either side of our sample mean here. So the question here, it's a true-false. The second estimate is much more narrower, providing accounting students a more precise information about starting salaries. And if you didn't want to pause the video, take a moment to think about that. Go ahead. And then when you unpause it, I'll reveal the answer. And that turns out to be true. Okay. Now, we've discussed this confidence level, 1 minus alpha, and that is inversely related to the level of significance. In fact, the level of significance is the complement of the confidence level. And this is user specified. You will decide what's the right confidence level to use. And fortunately, there are 3 main confidence levels that are used frequently by practitioners. They're very popular ones, and I'll show you those in a moment. But the way we're going to think about this diagrammatically is this level of significance, alpha, is going to be the area underneath that bell-shaped curve that's outside of the confidence level, right? It's the area outside of that level, defining the tail probabilities in our sampling distribution, meaning alpha divided by 2 is the area in just one of those tails in that sampling distribution. Okay, and we're going to think about this as really the probability that the sample mean lies in one of the tails of our sampling distribution. So let's go ahead and take a look at how we can think about constructing this 95% confidence interval. So I'm going to show you a pretty detailed picture here. So here is what we're going to do. Okay, we're going to be given some estimate X bar of our mean, and we're going to think about how far away do we need to define the upper bound and the lower bound threshold of our estimate. Okay, and the way we're going to do this, again, is going to be related to our utilization of the Z transformation, the Z score. And given our sampling distribution here of X bar, if we want to look at essentially defining our upper and lower bounds by these values along the x-axis in X space, okay, that will contain 95% of the data underneath the sampling distribution, right, inside that purple region. And what we're going to be able to do is, assuming that our sampling distribution is normal for the moment, we have to now figure out which Z value is associated with containing all of this area, this 95% area underneath the sampling distribution. So this is not totally unfamiliar to us. Okay, we recognize that if we're trying to capture 95% of the area underneath that distribution symmetrically on both sides, then we can divide that area in two and use our typical standard one-sided normal distribution table. So let's go ahead and do that. Okay, we're looking for a table value of 0.4750. And again, the question here is if we were using a 99% confidence level now. So here's what we're going to do. We're going to change it from 95 to 99. Okay, so 95 we saw on the last slide here corresponded to a 1.96 Z value. Okay, if there's 95% of the probability contained in the pink region, or the purplish region here, then that's going to correspond to us looking for the Z value that leaves only 2.5% area in that upper tail. Okay, so hopefully you can think about how you would do that. And in this next example, we're going to do the same thing, but instead of a 95% interval, we're going to do it for a 99% interval. So the question here is, using our standard normal table, okay, what value of Z would correspond to a 99% confidence interval? Now, hopefully you remember, if it's a 99% confidence interval, that means we're only leaving 0.5% in each tail. Okay, that's going to define that threshold upper and lower bound for our confidence interval. If we're looking for an area of 99% in the middle that we're trying to capture, okay, then the relevant table value for us is going to involve cutting that area in half, just like we saw in the previous slide. So if you take your 99%, you divide by 2, you get 49.5%. And if you look very close at the table here, you'll notice down in the row corresponding to a Z of 2.5 without accounting for the hundredths decimal place. Okay, we're getting some values really, really close. Okay, in fact, this 0.4949 value and the 0.4951 value are very, very, very close. And we could think about just taking more or less the average of the Z that corresponds to those two things to capture this. But this 0.4949 value there, that's really, really close to what we're looking for here. So we can use the table to get a pretty reasonable estimate that the Z value associated with this 95%, the 99% confidence interval here is going to correspond to a value of 2.57 using our standard normal table, using that one-side standard normal table. So as I mentioned before, there are several common confidence levels that are utilized. You might be concerned, oh, does that mean that 91% confidence level is going to have a different Z value than a 92, than a 93? The answer is yes. However, practitioners typically use one of the three confidence levels. We'll use either 90, 95, or 99. So you do not need to look these values up every time. Rather, I would recommend using a cheat sheet, or if you want to commit these to memory, you could. But these three values here, for a confidence interval, the 90% confidence interval corresponds to a Z threshold of 1.645. So that means the min and the max that defines that range, the min and the max range, are defined by 1.645 standard deviations to the right and to the left of your X bar sample mean estimate. Similarly, the 95% confidence interval. Okay, well, we remember from our empirical rule, if we go about 2 standard deviations out, that captures around 95% of the data. So it shouldn't be too much of a surprise that the z-value threshold here is about 1.96. Okay, standard deviations to the right and to the left of our sampling distribution, okay, assuming again that it's normal, captures 95% of the area underneath. And we just looked at the 99% threshold, and we saw that came out to approximately 2.57. Okay, so what we would like to do now is use that z-value in addition to some information on the variability of our sample data in order to actually construct this interval. Okay, so the next segment we're going to go through, how do we construct a confidence interval for the population mean mu if we have some reasonable assumption about the variance of our population. And again, it's kind of a catch-22. You're like, sometimes you know the variance, sometimes you don't. If it's a sample, typically we know it. If it's the population parameter, we typically don't. But sometimes it may be convenient to assume a value for the population standard deviation, the population variance. And if the population is large enough, we're going to be able to exploit the central limit theorem, which we had talked about in a lecture prior. And in the next video segment, we will show you how to utilize this formula at the bottom of the screen here to go ahead and construct a confidence interval given a particular point estimate. So hope you enjoyed. Stay tuned for more, and I will see you soon.